Ngalakin kadijan nyunga boja.
I think the online students will just kill me. Okay, we have 15 students online. Okay, so online students of the ELEC 5505, the Power System Analysis. This is Lu Jin. We are going to start our lecture very soon. So I want to just double check. Can you hear me? So Aaron, please give me a quick message. Are you able to hear me on Zoom? Again, for the SW students, our session will start at 5 p.m. So this session is now for another unit. May I ask you to leave this session? Thank you very much for the SW students. Okay, Aaron, give me a second. I'm going to set up. Share my screen. Okay. So everyone, just give me 1 second. We are going to start very, very soon. Okay. So let's start my microphone. Okay, good afternoon, everyone. So let's start our very last lecture of the ELEC 5505, the Power System Analysis. And you know, this is week 12, and the final week is here. And in this class, we don't have too much things to introduce. So our contents or discussion in this lecture will be divided into two parts. First part, so following the request from Professor Tarong, we need to finish one more section of the chapter 7. Even though that section is not important. After that, I'm going to give you a review of the contents of this unit plus important exam information. Okay, so I think last week Tyrone has already finished section 7.2, which is about the transient stability analysis. So he told me he has already done this part. And for me, we have only two small sections left, the section 7.3 and 7.4. Before we start the discussion here, so I can give you the information. These two sections are not important for you. The reason we have to finish this part is because it's related to the contents defined at the beginning of this semester, and this is important for you to get the EA credential for this unit. Okay, so we have to go through that. So for this part, we are going to introduce another model, so two-axis model, and this is also related to the transient stability analysis for the power transfer system. And in this case here, you can see we are going to introduce two systems, two coordination systems to the same power system to do the analysis. First of all, we need to understand why do we have to do that. So the analysis of more detailed synchronized machine models requires that each machine model be expressed in a frame of reference that rotates at the same speed as its rotor. The things like this one. Last week, we have already learned that the generator has a rotor rotated inside. But if, in some situations, the fault happens, so the generator has to adjust itself behavior to slow down or speed up so that the power produced by this generator can satisfy the demands of the power. And when we have this change here, we start transient or subtransient of the system. The most important thing we learned from last week regarding the transient stability analysis is about the angle of the rotor inside of generator. This part, the transient stability analysis, is important for exam. Okay, so you need to understand how to calculate the angle. So we talk about later. And because the rotor of the generator is rotating inside of generator, but in our past analysis, we always fix the so-called the theta angle. For example, we say the current, the voltage of the generator is in terms of the magnitude followed by the angle. The angle is phase angle of the voltage current stuff. But that angle is referred to a fixed coordinate system, which is the complex plan defined by the real axis and the imaginary axis. Because this coordination system is fixed, so in many cases, the angle calculation is the most complicated issue for such transient stability analysis. So because of that, we want to introduce another reference called the reference framework or the new coordinate system. This new system will not be fixed. It will be rotating together with the rotor so that the angle will not be a big issue. Because if you know the angle of the new coordinate system, then you know the angle of the rotor. This will be much easier. Okay? So this is the idea of this question here. But the question is, how can you define the new system? So here in the diagram, you can see we are defining a new DQ system. Of course, originally, regarding that traditional XY system, the x-axis, the horizontal one given in the diagram, is our real axis. The vertical axis is the imaginary axis. You have known this one very well in our past week's discussion. But now, the new system we are going to introduce today is called DQ system. The DQ system is in the same two-dimensional plan with the XY or real imaginary axis system. They are in the same plan, but they are not overlapping with each other. They are sharing the same origin, but the DQ system is rotating. It's not fixed. Okay. So how the DQ, these two axes are defined? D stands for the direct axis. Q for the coadjutor axis. So as I mentioned, this DQ system is rotating, but rotate with what? Okay, here, please read this one. The D axis is aligned with the rotor roll pulse. Where's my drawing pen? You can see the direct axis is aligned with the rotor pulse. The Q axis must be 90 degrees leading than the direct axis. So you can see we have the d-axis given here, and our quadrature axis is 90 degrees leading than the direct axis. And then you can have a look. The angle delta between the new quadrature axis with our traditional real axis, that delta is actually the angle of the rotor in the generator time by time. Okay, so this is how we define this new DQ system. Okay, now we got the question. Why do you want to introduce the DQ system? In other words, after you introduce the DQ system into this power supply system regarding the generator, what important quantities you want to calculate? So in this diagram, in this slide, you can see we have so many things. But I want to draw attention to one thing only, this one. EFD. E is the voltage, the internal voltage of generator. FD stands for the field voltage. So this is a field voltage for the generator. So during the transient stage of the generator, we will generate this field voltage. You may just ask me, is the field voltage good or bad? I'd like to say bad. In most of cases, the field voltage is unwanted voltage, happens during the transient stage. So we don't want it, okay? But in this discussion, in this section, we want to know how to calculate this field voltage. Before talking about details, I have to tell you, this topic involves a large number of background information and also a lot of mathematical calculation. Within this short section, in the very last week, we didn't intend you to let you to just memorize everything, understand a very comprehensive model, and know all the background information. This is not the target of this class. In this section, we just want you to know how to do it. That's enough. Okay. So let's start from the beginning of this this slide. So I got a question. Okay, guys, this is not the signal and systems. This is another one. Okay. Our class regarding the signals and systems will start at 5 p.m., not right now. Okay. First of all, what is the relationship between these two coordination systems? We said we have the so-called XY system. XY is the traditional real and imaginary axis, right? And the other one is the DQ system. So at the beginning of the slide, you can see we are introducing two matrix calculation formulas. So these two formulas are used to tell us how to do the translation between the two different systems. First of all, let's have a look at the formula on the top left. So on the left-hand side of the equation, you got VR and VI. R for real, I for imaginary. Okay. On the right-hand side, to the rightmost, you got VD, VQ. This is the voltage in the direct axis and the voltage on the quadrature axis. So actually, between these two vectors, the sine and cosine matrix in the middle is the transformation matrix for the conversion between two different systems. But why you have the sine delta, cosine delta, negative cosine delta, sine delta as the parameters or for the elements in this matrix? That's easy. Go back here. So actually, in this case here, for example, I focus on what is the voltage along the real axis. And the calculation by using the matrix rule is using the first row of this transformation matrix, multiple this vertical vector. So in other words, we can write VR is equal to the sine delta by VD plus cosine delta by VQ. Okay, I'm writing down this thing here. So in the graph, so we can draw this out. What is VD by sine delta? VD is the components of the voltage along the direct axis. For example, our direct axis is given here. VD is this vector along the direct axis. And where's the VD by sine delta? Delta is given here, but delta is also same with this angle. So the VD component multiple the sine delta is actually giving you this horizontal component. This comes from the VD component. The later one, VQ, by cosine delta. VQ is the component along the quadrature components. So I change my pen to here. This is the VQ. VQ by cosine is giving you this component. So along the real axis, so far we have a very short red color segment. We also have the green color segment. So how much is component along the real axis? That should be summation of these two terms. So this is how we derive this equation. For the next row, do the same thing. So in other words, we are doing this way to convert the vector between different systems to make them equivalent to each other. Okay? Sorry about that, guys. Just a small clash between the staffs. Anyway. Okay, this is a talk about how to do the translation. So the first graph, the first figure here, the first equation is actually the rule how we transfer the DQ system to the real and the imaginary axis. The other one on the right is the equation which is used to the other way around. So how to transfer the components from the DQ system back to, from the real and the imaginary system back to DQ system. So you can see this transformation matrix here is actually the inverse matrix of that. Okay, this is relationship. This is the first tool to help us to settle down within the two systems, so we know how to do the translation between them. And then we are going to start our analysis. At the bottom, you can see we are starting our discussion within the direct and the quadrature axes. So we got the two equations again. The first one, E is okay. E is the internal voltage of generator. EQ means what is the quadrature component of the internal voltage. The single prime means transient stage. Okay, so this EQ prime is indicating what is the quadrature component of the transient internal voltage of generator. Okay, the later one is ED prime. ED prime is similar thing. So what is the direct axis component of the internal voltage during the transient stage for generator? It's really long definition, but it should be easy to understand. Okay, and so EQ prime is known. EQ prime equal to what? Equal to VQ plus blah blah stuff. What's VQ? VQ is the terminal voltage of generator. You need to be very clear on these two different notations. So EQ and VQ. EQ is the internal voltage of generator, but VQ is the terminal voltage. So at the end of generator. Between these two things, what's different? The difference is these two resistor and reactance. This is RA, A for armature. RA is the armature resistance. XD prime is the transient reactance of the the rotor of the generator. So IQ, ID are just two different currents. So by doing this way, we are creating the relationship between the internal voltage of generator with the terminal voltage of it. To the equation on the right-hand side, roughly the same idea, but we are going to focus on the direct axis component of it. Okay? Again, this thing is not hard because we have known the internal structure of generator. The only new thing in this discussion is we are talking about the direct axis and the quadrature axis components only. Other things remain the same. And then we have two differentiation equations. So I think this part should be fun. As I mentioned, there are a lot of mathematical background regarding this part. We are not going to introduce the background in the lecture, okay? So knowing this one should be enough. But don't forget, our target is to determine the field voltage. After this step, we move on. So because your generator is working to convert the mechanical power to the electrical power, so in this slide you can see how this electrical torque and the power of electricity is evaluated. On the top of this slide, PE equal to TE by omega. This is used to evaluate how much the electrical power is. This electrical power equal to the product between the electrical torque multiple the rotation speed of the rotor of the generator. Omega s is the rotation speed in radians per second. The TE is called electrical torque. This electrical torque is the torque required to balance the external load. So actually the TE calculation formula has been given on top, which equal to VD by ID. V by I is real power. Actually this is used to evaluate what is the power at the terminal voltage of generator. VQ by IQ is the same thing, but along the quadrature components. So the summation of the first two terms is actually calculating what is the total required power at the output terminal of the generator. Later part, so is armature resistance multiplied by the I square. So that is the power required by the armature of generator. So in other words, the summation of all the terms in this equation is calculating how much power you need to consume before the terminal of generator. That is the torque, electric torque. This electric torque, TE, multiplied by the omega s will give you the electrical power we need for this equation. Okay? But you know, there's one exception. So in most of cases, the rotation speed is treated to be unit. And then in this case, omega is 1. So PE and TE are equal numerically. Like that. And then let's move on to the next part. So PE and TE are equal, right? In the next three equations, the first two are coming from the previous slide. We just copy them here again. And then the third one, you should have already known this equation. This has already been introduced in lecture last week. PM is the mechanical power. PE delta is the electrical power of the generator in terms of the rotor angle delta. PM minus PE means, okay, we have such mechanical power PM, we have such electrical power PE. The difference means between them is indicating the mechanical power is higher than the electrical power, or the mechanical power is lower than the electric power. That means just the difference between the two powers. But here you can see, if the PM minus PE is positive, what's that mean? That means the right-hand side will be positive. But on the right-hand side, omega s is the rotation speed. And the double derivative of the omega m. Omega m is actually the angle of rotor. If this thing is greater than 0, that means the angular acceleration and the velocity should be positive. This is indicating that the rotor of the generator should speed up. Again, if the PM is greater than PE, the actual mechanical power will make the rotation speed of the rotor much faster, so speeding up. Last week, when we studied the equal area critical, we said if this is positive, we have an acceleration area. If the PM minus PE is smaller than 0, we got deceleration area. These two areas should be equal. This is one of the cases. Talking about the relationship between these stuff. Okay. So keep going. So for this part, I don't really want to depend too much. The first two equations remain same as before, and for the next two equations, they are the same as the one we introduced in the last lecture. So it's just about the change rate of the angle of rotor. So this term is actually our ohmic stuff, the real-time rotation speed of the rotor, okay? And on top is the torque difference. But the torque difference will give you, this is alpha, because the change rate of the angular velocity give you the angular acceleration stuff, okay? So actually same thing. But in this slide, the most important formula is given here. The E. So at this state, the internal voltage of generator equal to the terminal voltage Vt plus J multiplied by the X cube by the current I. XQ is the quadrature component of the reactance. For this one, again, sorry guys, I know you are not very clear on this one, so I can just tell you the internal voltage equal to the terminal voltage plus this product, nothing else, because this is related to a lot of introduction regarding background. Okay, so this is just our background. Now you see the real part. From this diagram, you can see the structure of your generator. I have mentioned many times, so internal voltage, terminal voltage, these stuff are given in this diagram. This is the ideal voltage source, which is used to model the generator. The voltage across this ideal voltage source is the internal voltage. This is just inside of that machine, the generator machine. The armature resistors is given here, RA. This RA is used to model the resistance of the coil, the wiring of the generator. Okay, RA is given here. For such coil used in the generator, you have the transient reactance. So these two things are used to model what happens inside of generator. But what is the terminal voltages? Terminal voltages are just really the output voltage terminals from generator. They are given here and here. This voltage is the terminal voltage. We are getting the output voltage from here and here. Actually, you are not able to touch what's inside of your generator. Okay, this is all the important variables in this question here. What you are doing next here is really, really long equation, right? Super easy. This is a KVL. This is KVL. So let's just clean this part up and you can see what happened. Besides, we are using a KVL for this loop. The first term is about the voltage across the terminal voltage, this stuff. So this voltage here is given here, first term. In the next part, second term here, RA plus J by XD prime. This is total impedance of the armature in the generator. In other words, this RA plus J by the XD prime is total impedance on top. And then multiple the current going through that. So that means the second term is calculating the voltage across the armature impedance. This voltage. By the end, this very, very long equation is actually the internal voltage here. This internal voltage equation was introduced in the previous slide. Even though the formula is long, but I didn't require you to really understand and memorize that, right? So that's okay. So in other words, this is just a KVL, an easy KVL. And then in the steady state, all the derivatives are 0, so we can derive this equation. This ED prime and this ED prime are the same. So we can use the ED prime equal to XQ minus XQ prime IQ to substitute the EQ prime in this equation. After you do this, so you can see this negative XQ prime and this positive XQ prime can be cancelled. Then we can derive this relationship. Okay. Okay. So move on to the next one. After you calculate this one, you will get the E term and then the angle delta. This angle is the angle of the rotor, or in other words, the angle of the generator. It can be derived like this stuff. I know this part is boring and you guys just got tired on this. Let's quickly see one example, okay? And actually, in the conditions of the question, we just gave all the important data as condition. So I'm not going to read through this one, okay? Let's have a look how to solve that. First of all, the first several steps are pretty easy. So in this question, we want to evaluate what is the equivalent impedance. So XEQ, my fault, equivalent reactance, okay, XEQ. So we got such relationship. So this calculation is actually evaluating the total equivalent reactance of the whole block. Okay, so some are in series, like the X13, X23 are connected in series, and then in parallel with the X12. Then the whole block is in series with XTR again. So by following this relationship, we just evaluate what is the equivalent reactance of that. And next, we evaluate what's current by using the power. This is easy as well, okay? Once you finish this stuff, So we are using this formula to evaluate the terminal voltage of generator. Okay, the later part should be easy. See here, this is the current, this value. Current multiple the total equivalent reactance give you a voltage, like that. Okay, so finally the terminal voltage is given like that. After you got the terminal voltage, we are using which formula? We are then use this formula E equal to the terminal voltage Vt plus J by SQ multiple the current to evaluate what is the internal voltage of the generator. So that formula is used here. The reason we want to evaluate E is from the internal voltage, you can derive the angle of your generator. After this angle of the rotor of the generator is known, very last step is to evaluate EFD. So this is the field voltage. There are a couple of steps, but this just do the translation between two different coordinate systems. So nothing new, okay? I know guys, this calculation is a bit long, but most of steps are just using the formulas we gave in the first slides. Just that. It should be easy, okay? Section 7.4 is another topic about the exciter. For this part is just general introduction. I don't want to waste the time of the lecture to go through this part. I don't think we will have any questions in the exam related to the chapter, the section 7.4. So for this general introduction, please go through that by yourself. We just introduce what is the functionality of the exciter in the AC circuit, in the AC power system, okay? Okay, everyone, so I think so far we have done all the contents of this unit. Any questions? Okay, 3:30. So everyone, after this part, we are moving to the next part of this lecture, so the revision of this unit. And let me switch to our revision thing. I plan to use about 20 minutes to quickly go through the contents of this unit and give you some hint maybe, and happy to record something. And then I'm going to give you the exam information. Then we finish class. So in other words, this lecture will be very short, okay? And in this unit, we studied in total 7 chapters. Chapter 1 is pretty general. It's just about the review of some fundamental properties, rules, quantities, variables used in the AC circuit. For example, what is the impedance, what is the admittance, how to calculate concave power, the phase angle, power triangle, inductance, capacitance, all this stuff. So chapter 1 is very fundamental. Please do not ask me, will the chapter 1 content be covered in the exam? Yes, it will. It will be covered in all other chapters. Okay, you have to know this very, very well. For example, in one day you tell me, okay, after exam you come to me, I don't understand what is angle. Sorry, I can't help you. Okay, so maybe I have to say, so welcome back next year. Okay, so I don't want this to happen. So chapter one must be covered, and maybe we will not have one particular question ask you to calculate the impedance of the capacitor, impedance of the inductance, because the contents of chapter 1 have already been mixed within the other 6 chapters. We can't separate this chapter from others, okay? We don't have time to go through this one, so it's really simple, okay? Chapter 2, transmission lines. I hope you guys have a good memory regarding our class test. In the class test, there is one transmission line question, and how did you feel? That question is pretty simple, right? I didn't give you the long transmission line model because that's really terrible, right? So you should appreciate me, okay? So actually, in the chapter 2, we studied a couple of things. First of all, 3 different transmission line models: short, medium, long. So Stuart, I hate you on that day because you asked me, for that 100 kilometer transmission line, is that a long one or medium one? Don't ask me that thing, because we have very, very clear definition regarding under what kind of range of the transmission distance, what kind of model we should use. So 80 kilometers, 140, something like that. That question, I didn't answer you, right? Yeah, that's because this is good, right? And also for the open book, you can check this one from the reading notes, right? Yeah. So this thing here, so 3 different transmission lines. Same thing. In the exam, if you have such questions, I will not tell you what model you are supposed to use. You need to know this by yourself. Okay? So transmission line model, 3 models, plus ABCD model. In other words, 2-port network. Okay? So actually, the 2-port network can be used for all 3 models, right? So you are requested to understand this stuff. Before moving on to the chapter 3, I want to remind you one thing. Yes, understanding that ABCD model should be easy, and for different type of the transmission lines, we have different parameters. But do you remember, regarding long transmission lines, for that model, when you use ABCD model, there are some particular functions, like the sine, cos, something like that. You didn't use that too much. I know you use sine, cosine, tangential very well, but sine or cos, not easy, right? Shortly, we can just have a look if these formulas are given in the formula sheet, but I don't think so. So we just gave you SINH, COSH. But what do they mean and how to calculate? For example, the cos. Guys, can you remember what's his formula? Half of the summation between 2 exponential functions. Sine is half of the difference between the 2 exponential functions. I'm not giving you this thing. You need to memorize that by yourself. Okay, this is the transmission line chapter. Chapter 3, transformer. So I think at least for the chapter 3, we are thinking about some ideal transformer stuff. But for this chapter, what will be important, guys? Can you remember? Per unit system. So if we give you some absolute real values of the like the complete power, voltage of different regions within your power system, and I request you to convert that into the per unit system based on the given base complete power, base voltage. So how to do that? So if your power system doesn't have any transformer, that's so easy, because you can just share the same base power and base voltage for the whole region. That's okay. But if you have the transformers in the system, the transformer is used to change or transfer the voltage. If you define for a particular region, the base voltage is something, and if this region is connected to another region through the transformer, the base voltage will be changed. But the base power will remain the same for the whole power system. Okay? Then this involves calculation. I have now done the marking of the test 1, so some students did a very good job. But I suppose because, first of all, in the class test, you got an open book. You can check solutions. Secondly, the question given in the test 1 was so easy. It's not so hard. But in the final exam, because you have learned this thing for more than 10 weeks, I suppose you will get a lot of experience on that. The question may be a little harder than the class test. Okay? Okay, this is chapter 3. Chapter 4, power flow analysis. In the power flow analysis, quickly, chapter 4. So actually, I gave all the table of contents for different chapters. So first of all, for the linear and the nonlinear power system models, power flow problems, and admittance matrix, that is the first question in our mid-semester class test. Okay, I think all of you did a good job, so I'm pretty happy. Okay, you must be able to know how to calculate the admittance matrix based on the impedance given in the question, and then power balance equation. Okay, the first 4 sections of chapter 4 are pretty okay, not so hard. Right? The hard parts are given next, GS and NR, so Gaussian and Newton. In the question number 3 of the class test 1, we did have this question, and many of you didn't do well. I understand calculation is a big problem, but when I check your formulas, I found many of you wrote wrong thing. Not only the calculation, but also formulas. In other words, you are not really good at this theory. So for this question, I can almost 90% guarantee you will have similar questions in the exam. Okay, make sure you are good at this. One more thing. So in the section 4.5 and section 4.6, the GS, the Gaussian one, and Newton, these two methodologies. The Gaussian one is okay. We can just run the test questions on that individually. But for the second one, the Newton-Raphson methodology, actually this part can be mixed with our fault system analysis. So remember at the beginning of class, I mentioned we have the equal area theorem. Remember that? In that part, you will be required to calculate the angle, the critical angle theta or delta, whatever. Then you have to use the iterations to solve that because you do not have computer in your hands. By then, the Newton-Raphson method will be used. In our tutorial of, so I can't remember which chapter, and we have a similar question there. So you need to understand how to use this particular methodology to solve the fault system critical angles. Okay, we talk about that later. Okay, this section, this is chapter 4, power flow analysis. Actually, the chapter 1 to chapter 4 have already been covered in our class test. So you guys should have already be very familiar with these contents. And then in the later part, after we finish class test, we move on to the new contents, the fault system. The first fault contents is in the chapter 5, symmetrical faults. This part should be pretty easy compared with the chapter 6. Because for the three-phase power system, all three phases got a fault at the same time and at the same position. So the three phases are all connected to ground. So this is a symmetrical fault. So the circuit analysis are really simple compared with the asymmetrical fault. But regarding this chapter, what you need to know? Because you got balanced system, and all three phases got the same fault at the same position. So we can just focus on the analysis of the fault within one single phase, and then extend it to all three phases. So this is the idea of question. But regarding the approach for the circuit analysis, we have three different methodologies in this chapter. The first way to analyze this symmetrical fault in one single phase is so we call that as a direct calculation. That means just KCL, KVL, nothing else. But I hope you remember this procedure. That part is pretty with suffrage because you have to use a lot of KCL, KVL to determine what is the voltage for different components in the circuit. Okay, and then calculate that before the fault, after the fault, during the fault. So that part is pretty challenging on the calculation stuff. Okay, so this is a direct calculation, the first approach to this symmetrical fault. Because the calculation for the direct calculation is hard, and then we introduced the second approach, which is the, you guys can remember that? Superposition, good, superposition. Remember, so at the position of the fault in the system, we introduced a pair of the equal voltage sources into circuit. And then we separate this circuit into two. In one of them, there's only one fault voltage source. But on the other one, there are three. And the value of the introduced voltage source will be equal to the fault voltage. Based on this one, we do the simplifications to derive the answers. This can save a lot of our works. Okay, so this is the second approach using the superposition. What is the third one? The third approach is called Rick equivalent circuit, R-A-K-E, Rick equivalent circuit. That is based on the superposition, but can be easily applied to multiple branch systems. So for this part, I believe some of you may have already forgotten this one. So we're going to do the revision. So please just read all details. Okay, this is chapter 5. Okay, now you got a very hard chapter. So a symmetrical fault analysis. And in this chapter, we are going to analyze the system with different types of faults. So I think in the symmetrical fault, we have three types of faults. First one, so single line. So out of three phases, right? Single line to ground is the first fault. Second one, so you have three phases, right? Out of the three phases, So 2 out of 3 got short connection. This is a double line fault. Third fault type is out of 3 phases, 2 of them are grounded. So it means double line to ground. Okay, so maybe the name is slightly different, but the idea may be like that. Okay, so 3 different fault types. Regarding this chapter, what are the important things? No, that is really simple, too simple, not 4 types. I believe you enjoyed it. Let's remember 3 different sequence networks: positive sequence, negative sequence, and 0 sequence networks. Yes, this is really hard part. Okay, you must be very good at these 3. We call them a set. Okay, a set of the sequence networks, which consists of positive, negative, and 0 sequence. And regarding this sequence network, the hard part is for different components used in your system, based on different connection types or styles, the equivalent circuit will be different in different sequence networks. For example, if you have a generator delta connection in the 0 sequence network, is that generator connect to ground or not? Something like that. And also, if you got a Y connection pattern for the generator, and its neutron is connected to the ground through some reactance, so what will be equivalent reactance in the 0 sequence network? For the transformer question, much harder than generator. If you want to draw the equivalent 0 sequence circuit for the transformers, each transformer have 2 sides, and each side have 2 possible connection patterns, delta or Y. And for the Y pattern, there are 2 options. So neutron connect to ground, or neutron not connect to ground, or neutron connect to ground through some resistance or reactance. There are so many options and so many possibilities. I have to say, this part is important. You must know them very well. You do not have time to learn this thing in the exam. If you do so, I think at least 1 hour will be used to learn this stuff. You must learn this one before, and must do a large number of exercises to make sure you really understand this topic. Okay, this is one. But in addition to these different sequence networks, there's one more thing. After you draw the equivalent sequence networks, what do? This is just first step. So after you draw these sequence networks, next thing is to introduce the different types of the faults into this sequence network to do the analysis. We mentioned at the beginning, for this chapter, you have in total 3 types of the asymmetrical faults. So when you introduce different types of the asymmetrical fault into the system, the circuit between the 0, positive, negative sequence networks will be different. Learn this stuff, please. I know you guys may lag behind with the progress of class, but we have a large number of the tutorial questions. Do them out. Okay, try them out. Okay, this is chapter 6. If you want me to say, out of these 7 chapters, which chapter is the hardest one, I'd like to pick up the chapter 6. Okay? Higher than 0, lower than 100. Chapter 7. Okay, now we have done the hardest chapter. Now we got easier. For chapter 7, economic dispatch of the power and the transient stability and the control. So actually, in the first half of this lecture, regarding that field voltage stuff, like the transient or the transient analysis, and also exciter stuff, that partially belong to the control issue. The transient stability and the economic dispatch in this chapter are also important, but much easier than the chapter 6. Okay. So regarding the economic dispatch, I think in the tutorial this week maybe, I talked about this, right? And regarding the economic dispatch, there are 3 models. So first model, of course, all 3 models are about the optimization regarding the running cost of the generators in the system. And the first model is about the ideal model. That means we just need to find the optimized result, but without any constraints. So that means the generators in the system are able to produce as much as energy, power. No limitation at all. Based on this one, we are going to evaluate what is the optimal running cost of DSA. So lambda is used, right? And the second model for this part is about some constraints, the constraint optimization model. In such case, the power generated by the generators cannot go infinitely big. It will be constrained within a small range. Based on this one, how to determine the optimal value of the lambda running cost, incremental cost, and calculate the cost value. This is a small extension. So we mentioned actually if you have such constraint applied to your generators, normally the running cost depends on the generator which is not running on the constraint value. Okay, this is the second model. Third one is another extension. So you have the generators in the system, and we are going to focus on what is the optimal running cost of the generators. But when the power is transmitted in the system network through the transmission lines, so we have the loss of the energy, the loss of power during the transmission. So if you have the loss of power between the transmission, so in more than 99% of cases, the power loss function will be given in terms of the real power produced by these generators. Then how to do the calculation? Okay, so this is the case for the topic of the section 7.1, economic dispatch. For the very last section, so transient stability. How to say that? It's very hard for me to judge if it's hard or easy. For me, it's easy. For you, I'm not sure. So I'm not sure how much you understand that. Because for this topic, transient stability, the idea is easy. We just want to test if you understand how to use the equal area criteria to determine the key angles. This is just the key thing, the key component for this section. But regarding this, the plotting of curves, the real power curves, the plotting of the mechanical power, and the sine function, and how to use the Newton reference method to determine the angles, that's really a lot of topics. If you understand this very well, if you are able to conduct the fault analysis, so this topic is easy. But if you think, okay, I don't understand what does fault mean, and I don't understand what will be the circuit after fault happens in my system, sorry, you will get 0 marks for this question, because you can't start it. So the fault analysis is a preliminary condition for this question, for this section. So make sense? Yeah. No. This information is not given. I mean, it's not given in the question. Depends on what system you have. Okay. Sorry for that. Yes. Okay. But I think in the later 3 chapters, chapter 5, 6, 7, we focus on the fault analysis in all 3 chapters. And when I want to test if you understand the fault analysis in your system, I will focus on the chapter 5 and 6, the symmetrical fault and asymmetrical fault analysis. When we move on to this section, so my focus will not be the fault analysis. My focus will be the stability of the transient stage of the system. It's about how to use the equal area criteria, that's it. So that's, in that case, the fault problem is not a big issue. So you understand me? Yeah. Okay, that's just the overview of all the contents of this unit. Next one, exam information. So the time and date of the exam will be starting at 9 a.m. on the 2nd of June. So it should be Wednesday, right? Wednesday of the week 1. So everyone, this one, I'm not sure if my information is right or wrong, because I got this information weeks ago from the exam office. If they updated something, I am not sure. Okay, please double check your personal exam timetable. Okay, and also we have the face-to-face students. We have the online students. You are going to sit the exam in different platforms. So I don't comment on this thing. So please double check and follow the instructions given by the exam office. Okay. Okay, the time and date are known. Next one, duration, 2 hours, very standard one. And the format, sorry guys, I apologize for this. Closed book exam. I know this totally different from your expectation. You wanted to have the open book one, just like the class test, right? I tried. I gave the open book request to exam office, but unfortunately, I was rejected. The exam office requested me to use the closed book test. The reason of this one is because we have the online students and the face-to-face students. So for online one, we can't run the open book exam, and we have to keep two groups students got fair treatment. So if the online students have to take the closed book exam, so face-to-face students have to take the same style, so closed book exam. But the good thing is, except last year when we have the COVID-19, before last year, we always had the closed book exam. So this is fair, except last year, okay? So I don't think this is really a big issue, but everyone please be reminded, in this unit, we have closed book exam, not open, okay? The closed book one means no iPad, no laptop, no phone, no paper-based documentation, no any learning materials, just yourself, okay? Calculator, yes, and pen, and your answer, something like that. Yeah, formula sheet will be given. So again, another issue. We have two different exam modes, so face-to-face and online. I just kept receiving updates from exam office regarding what will happen in the exam, online exam. And so far, the latest information is for face-to-face students, you do not need to print out the formula sheet by yourself. So you do not need to. So when you go to the exam menu, the exam invigilator will give you two things. One is exam paper, and the other one is the formula sheet, formula booklet. You just go there with your personal belongings and do the works, just that. For the online students, as I know, the new exam platform may have some issues. They said the attachment of the online exam may not be accessible in some cases. I don't understand why, because I have never used that before. So just in case, so all the online students, you are required to print out your own formula booklet before going to the exam. And when you go to the exam, so in front of computer, the exam invigilator will ask you to show all the papers in front of camera, and the invigilator will check. You have only the formula sheet in your hands, and plus maybe some draft paper, must be blank. So this will be checked person by person to guarantee you are taking the closed book exam, okay? Again, everyone, this is just the information. And officially for me, I didn't read any official documentation to me because I don't get access to the online exam platform. I know nothing. I just asked about admin, and they told me regarding the latest information for online student exam. So exam office and the admin staff will send you an email very soon, or maybe you have received it. So please follow the instructions given in there to prepare your site, okay? Okay, this is about the formula sheet. The sample formula sheet has already been uploaded on MS, but maybe I forgot to enable that folder to you. So after this lecture, I'm going to just enable that exam preparation formula folder on MS. So the sample formula sheet is given there. So everyone here might take this opportunity to remind you. I suggest you to go through the 8 or 10 pages formula sheet and make sure you know what formulas are given. The reason is I want you to know which formula are not given, so that you can prepare that by yourself. Okay? Don't think, okay, so formulas given in the whole unit reader must have already been in the formula sheet. No, we didn't guarantee this one. Okay? So for some formulas, you have to memorize that by yourself. For example, Koch, shine. Okay, how to do that? And also, for example, for the let me think. In the economic dispatch part, regarding the third model, we set transmission line power loss, so something were not given there. And also I think which part is it? For the asymmetrical fault part, regarding transformer, the generator, motor, or something like that. So what are the equivalent components used in the zero sequence, positive sequence, negative sequence network? For that part, I can't remember details. You guys need to double check. So in other words, there are so many things. I can't put everything in my mind now. So you need to check all details before going to the exam so that you can easily find everything in the test, in the exam. And also you can just prepare what formulas are not given, okay? Okay, this is about the formula sheet. Calculator. I don't think I need to say anything. You have already known how important a good calculator is in this unit. You must have the calculator which can be used to calculate the angle, the magnetic stuff, something like that, right? And please make sure your calculator model is approved one from the list given by the faculty. Okay. Cover the contents. You have known that from chapter 1 to chapter 7. Okay. And finally, regarding the exam consolidation, so far I have not confirmed time with Tyrone, and we need to just have chat regarding this one. Before we give you any information, so everyone, if you have any questions regarding the contents of the exam, please send email to either Tyrone or me. So we will try our best to get back to you as soon as possible. If we can just handle these questions from students by using email or maybe Zoom connection, maybe we will not hold the consultation session. Okay. Okay, everyone. I think this is everything from me. So, any other questions you want to ask? Yes, of course. So all the materials have already been given into that exam preparation folder, RMS, including the sample formula sheet. This so-called sample formula sheet is exact same as the one you will see in the exam. Okay, sample formula sheet, and 2 past year exam with solutions. Just one more thing. Oh yeah, the very last thing is this slide. I will put this slide into that folder as well, just in case something didn't show up and want to check out details. And also, this revision lecture is recorded. So if you want to double check some details, go to the lecture capture system and listen to it again. Is that okay, Aaron? All good? Andy, yeah.
So would it be about like 5-6 questions for 2 hours?
Oh, really good one. Really good one. I forgot to mention that, right? You'll be given 6 questions. 6 questions within 120 minutes, roughly 20 minutes for each question. Of course, some questions are pretty simple for you, so you can just use less time. If you save some time in easy questions, so this time will be used for hard questions. Okay, so this thing here. Maybe I can give you some study suggestions. First of all, okay, the very last thing we need to say in this revision lecture is how to prepare for the exam. First of all, to say the truth, I'm not sure how you study this unit. I know the attendance of the lectures and the practical classes are not very high, so I believe most of you are watching the videos at home. So I believe you, I trust you. So I suppose you are learning the contents of this unit. To say the truth, some calculations or some sections in this chapter are not so easy. You have to take some time to really read through the lecture notes and slides. And I think some example, to say most of the examples given in the lecture slides are very helpful. And you have done our class test. You can see the questions given in the class test are very similar to the ones given in the lecture examples and the tutor part. Okay, so if you are able to manage example of lectures, tutor questions, past year exam, our class test, you should be fine. But my thing here is, I said, if you are able to manage these questions, the manage means you are able to solve the questions without any help. So if you want to test your own capability, don't check any lecture notes. Don't check any notes. Don't read the solutions at all. Just take the question out. Do it. Make sure you can finish it within 20 minutes. If you can do so, good. But if you think, okay, during the approach to the question, I still have to check the lecture notes, or I take maybe 50 minutes to finish your question, that is not good. Even though you got the correct answer, that is really too long. That means you need help to finish the question. Then that means you are not able to manage these questions in the exam. So keep trying, okay? And we mentioned that there are about 6 questions, and all 6 questions are the calculation questions. So we do not have the multiple choice questions or short answer questions. So just long questions, do the calculations. The style or the format of these questions are very similar to our tutorial part. So if you want me to give you a suggestion, I suggest you to go through the tutorial questions, okay, in the details, very details, okay, and make sure you understand why this number is using the line-to-line voltage, why the other number is using the power of the single phase, or why this equivalent fault circuit like this. So all these things are important. If you forgot something, you may just double check the videos from the tutorial part. So over the whole semester, when I go through the tutorial questions, because the time of the practical class were too short, only 45 minutes, it's impossible for me to go into the very single step. So in my classes, I tried my best to give you some hint or idea. So why the question is solved like that. For the calculation part, you can check the solutions by yourself. So this is just the idea of all the practical classes in this unit. So if you forgot how to solve the question, or when you check the solution of the tutorial questions, you don't understand why. Okay, check the lecture notes or watch the video of the tutorial and the lectures. They must be very helpful. After watching the video, if you still cannot check out or understand the questions, email Professor Tyrone or email me. We can give you some quick hint. Is that okay, everyone? By the end, everyone, thank you for attending the lectures and the practical classes of this unit. So Professor Tyrone and myself are appreciating your attendance and participation. And we all hope everyone got good marks, not only in this unit, but also in all the units you are studying in this semester. And if you have any questions, I think Professor Tyrone and I will be more than happy to help you. So best wishes to your exam, everyone. Thank you very much. Okay, online students, we have finished our revision lecture. If you have any questions regarding the contents of this unit, please just feel free to contact Professor Tyrone or contact me directly. Thank you very much, and good luck for you. Just one second. Yes, we can do that later. So far, I think many groups have done this. And again, I do like to get attention, but I asked the UNC notice. They said normally the full-time revision will not be allowed to set on weekend or semester, except some special situations or environments. So, because many groups can finish the works, so I don't think it's a good idea to just give attention to everyone to the weekend. So if you really have some special situation, let me know. That's all.
Yeah.
Sorry about that, but
Yeah, that's right.
like exam what they say, like the EMS what they say, just take it out of the number. But just follow the instructions.
It's still 11 a.m.
So again,
It's still 11 a.m. I mean, due at 11 a.m. on Friday.
good question. So what did I say? Yeah.
I think it said 11 a.m.
Yeah, zero, yeah.
But guys, remember here, so within 24 hours after the due time, you will not receive the penalty. So in other words, if you submit your work by 11 a.m. on the following day, you are safe. But why? But fine. So is that okay? Yeah.
Are the 6 questions equally
questions, there are some hard questions.
You said, yeah, 20
The-
minutes each, then.
Roughly, the 20 minutes each question, but the marks will be different. I said for easy questions, you can save your time. So using shorter time to finish easy questions. The save time will be given to the hard question because the hard question was more marks, right?
And obviously, the answer booklets will be different from the.
Should be different. So in the exam paper, so I just give you the question by question without the attendance basis. So you'll be given, I said two things, right? Three things: formula sheet, exam paper, and the answer booklet.
Yeah, this 100 minutes is only giving.
So I think the space will not be sufficient if I just give the space in the exam paper. So separate booklet should be better. Yeah, all good. Kimo, are you still here? Am I? Hi, Kimo, are you here? So regarding the exam submission, I suppose we are doing the same way, but I'm not the expert of that. I don't know to say truth. So the exam office or admin will send you update very soon, before exam, definitely before exam. So you know that very soon. The reason I didn't mention it is because I got totally no idea on this issue. I don't know the answer. So please wait for the instructions from exam office. Thank you very much. And Pei Feng Sun, yes, I know your issue. I know you want to talk with me, but I'm really busy today. I don't have time. So please send me an email and we can make another appointment at another time. Thank you very much.
Thank you.
No worries, guys. Thank you very much. See ya.
I think the last time we see each other is like the fact class.
Ready?
Because that's the final.
No, 444, right?
Yeah.
No, you can't do it. So in the exam folder on MS, 4444, I wrote the credit class of this week. This time we don't have credit class. And we don't have any classes now because only the chapter 1, 2, 4 are covered. But all the credit class of these three credits have already been done. And submissions of the three questions, the later questions were online. So we don't have any chances for this one. But now if you have any questions, okay? Yeah.
I've got a question. So, is the power protection something covered in that? Because you didn't mention
You know, this question is hard to answer.
Yeah.
Breaker is part of the element used in the circuit protection.
Okay.
We do have breaker.
Okay.
But if you ask me a particular topic,
Yeah.
like how to design this protection
Yeah.
system, it's too big.
Yeah.
That's too big.
Because there's no formula either. I don't know.
So it's very
I think
hard.
it's just mathematical for like
Yeah.
after
So different levels.
cycle.
Yeah, yes.
So the breakers.
Just regarding the transient, sub-transient, different things, right?
Yeah. Right. Yeah.
So actually, the transient and sub-transiency will be tested in another questions, like the symmetrical forcing or the other one. For the protection sake, we don't have particular question on that.
Yeah.
Yeah, because you didn't hear I mentioned, right?
Yeah. Yeah.
So actually, when we go through the table of contents,
Yeah.
I mentioned the important points.
Yeah.
They are important.
Yeah.
Other things, maybe more or less be involved, but not too much. It's
Yeah.
tiny.
Yeah. Yeah. Fair enough.
So is everything okay?
Yeah. That's
Yeah.
fine.
Yeah.
That's fine. Thank you.
No worries.
More weightage on the contents after the test, or it's like balanced? I know I'm asking too much.
It is what I'm doing because I think the so-called classical exam will shock many students. So I'm trying to just use your class test mark to balance this exam because I think performance exam will not be good.
Is it required to pass the exam to pass the
No,
exam?
they don't
Or
have
it's-
such requirements. They don't have. So it's why we want you guys to do good in the assignments because there are total 30 marks in the assignments, right? Yeah. But you guys should be fine, so don't worry about too much. So wait, that's all.
Like one last question, what is the reason for not having so many formulas on the sheet? Like,
We have tried our best to put as many as equations in, but for something, we may treat them to be the preliminary knowledge, like the cost. I think in some retreat, we think such equations have already been given. Just like we do not have to give the cosine or sine thing again in the
Yeah.
formula sheet. The same is
No, but say,
They
for
have to
example,
memorize
yeah,
all the
this was what I used
the
during my
equivalent
class test.
circuit,
So
something
I
like that.
wrote down everything because
Yeah.
it was an open book test. And obviously, this part, obviously, because it is
Yeah.
not, it was
You
not
have to
Yes,
memorize
just the
lots
one
of
I gave
things.
you.
yeah.
I can't
Yeah,
remember.
yeah, that's it.
It's just- yeah.
I think
And I have
But-
like everything here.
yeah.
You know what? You know what?
Even,
So
even things like this one, right? This is what I actually emailed you about this regarding. the
remember, I emailed you a long
Yeah.
thing. Give you
Yeah.
information.
But now the thing is, if I want to use this, I have to remember it, right? Like because I'll only be given this one and not this one.
This is only for the long transmitted table, right?
Yeah, but
Did I remember? I told everyone. That thing is not given. So remember that. Yes, you have to. Okay.